Something was picked up 750 light years away from Earth, and the scientists who found it couldn't explain it, not because the data was incomplete, not because the instruments malfunctioned, but because what they were looking at simply should not exist. When the team at the University of Chicago pulled the readings from NASA's James Webb Space Telescope, the room went quiet. Then someone broke the silence. The words they used were not the language of peer-reviewed journals or careful academic restraint. They said, out loud, in a room full of the world's most brilliant minds, "What the heck is this?" That question was not rhetorical. It was genuine. And as of today, nobody on this planet has been able to answer it. There are moments in the history of science when everything we thought we knew gets quietly rearranged. Not dramatically, not with press conferences and flashing cameras, just quietly, in the data, in the numbers, in the spectral readout of a telescope hovering 1,000,000 miles from Earth in the silence of deep space. This was one of those moments. And what triggered it was a planet, if you can even call it that, a bizarre lemon-shaped world, orbiting a dead star at a speed and distance that our models of physics say should be impossible to survive. And yet, there it was, spinning, existing, defying everything. It is officially designated PSR J2322-2654b, a tidally locked exoplanet orbiting a millisecond pulsar called PSR J2322-2652, located in the constellation Sculptor. The name is cold and clinical. The reality it describes is anything but. What the James Webb Space Telescope revealed when it trained its infrared eye on the system was not just a strange planet. It was a cosmological anomaly, a crack in the foundation of how we believe the universe forms worlds. And the deeper scientists look into it, the stranger it gets. Let's start with the star it orbits, because the star itself is unlike almost anything we've ever encountered. The planet orbits a star that's completely bizarre, the mass of the sun but the size of a city, said Michael Jang, the principal investigator on this study from the University of Chicago. Think about what that means. The sun has a diameter of roughly 865,000 miles. Now imagine compressing that same mass, all of it, into something the size of a mid-sized American city, maybe 10 to 15 miles across. That is a neutron star, the leftover core of a star that died in a catastrophic supernova explosion, collapsed under its own gravity until protons and electrons were crushed together into neutrons so dense that a single teaspoon of neutron star material weighs more than 1 billion tons. This is the object that PSR J222-2650b calls home. But this neutron star is not just dense. It is spinning. The pulsar completes around 300 rotations per second, equivalent to 18,000 rotations per minute. For context, the most powerful engines on fighter jets spin at a fraction of that speed. This star, the size of a city, the mass of a sun, is rotating 300 times every single second. And as it does, it fires twin beams of electromagnetic radiation from its magnetic poles, sweeping them across the universe like the beam of a cosmic lighthouse. This is what scientists call a millisecond pulsar. And it is one of the most violent, extreme environments in the known universe. The question that should be screaming in your head right now is, how does anything survive orbiting that? And here is where it gets worse. PSR J2322-2650b is extraordinarily close to its star, just 1 million miles away. In contrast, Earth's distance from the Sun is about 100 million miles. Because of its extremely tight orbit, the exoplanet's entire year, the time it takes to go around its star, is just 8 hours, 7.8 hours. That is 1 complete year on this planet. While you sleep through a single night on Earth, this world has already lapped its star and begun the next orbit. The velocity required to maintain that orbit while remaining gravitationally bound to a neutron star at that distance is almost incomprehensible. And yet the planet is not only surviving, it is there, intact. And apparently it has been there long enough to develop an atmosphere that no one has ever seen before. When the Webb telescope captured the light spectrum from this planet, the scientists expected to see what they always see on gas giants in close orbits: water vapor, methane, carbon dioxide. The familiar chemical signatures that have appeared across hundreds of exoplanet observations. Instead of finding the normal molecules we expect to see on an exoplanet, like water, methane, and carbon dioxide, we saw molecular carbon, specifically C3 and C2, said Michael Jang. Those are forms of carbon that don't just bind to themselves under ordinary circumstances. Molecular carbon, carbon bonded only to other carbon atoms, is chemically promiscuous. At the temperatures found on this planet, carbon will grab onto anything: oxygen, nitrogen, hydrogen, anything. The only way for molecular carbon to dominate an atmosphere so completely is if there is almost no oxygen or no nitrogen present at all. And that is exactly what the data showed. Of approximately 150 planets that astronomers have studied inside and outside the solar system, no others have any detectable molecular carbon. None. Out of 150 worlds across decades of observation, not a single one looked like this. And then, in the constellation Sculptor, 750 light years from Earth, there it is, alone, unprecedented, unexplained. The temperature range on this planet tells its own story of extremes. Temperatures on the planet range from 1,200 degrees Fahrenheit at the coldest points of the night side to 3,700 degrees Fahrenheit at the hottest points of the day side. Think about that temperature gradient. The difference between the coldest and hottest regions of this single world spans 2,500 degrees Fahrenheit. For reference, iron melts at around 2,800 degrees Fahrenheit. The day side of this planet is hot enough to begin approaching the melting point of iron, and the night side, which would feel cold by comparison, is still running hotter than a ceramics kiln. There is no temperate zone, no habitable region, no calm. This is a world of absolute, unrelenting extremes. And it has been that way, in all likelihood, for millions of years. Now let's talk about what is happening inside this planet. Because this is where the story becomes something that sounds less like science and more like science fiction. As the companion cools down, the mixture of carbon and oxygen in the interior starts to crystallize, and pure carbon crystals float to the top and get mixed into the helium, according to Stanford's Roger Ramani. Pure carbon crystals, floating upward through layers of helium. PSR J2322 to the 26580b has so much carbon in its atmosphere that scientists now believe the high pressures found inside the planet are likely to compress that carbon into diamonds. And such diamonds are likely to be falling towards the planet's core like rain. It is raining diamonds. Somewhere inside this strange lemon-shaped world, orbiting a spinning dead star 750 light-years away, diamonds are precipitating out of the atmosphere, forming in the crushing pressure of the interior, and falling like rain toward the core. The total wealth represented by the diamond content of this single planet would be so astronomically large as to make every diamond mine on Earth look like a pebble in comparison. But of course, that is beside the point. The point is that this is physically, chemically, and atmospherically unlike anything we have ever encountered. And we still don't know how it got that way. This is where the scientific mystery deepens into something genuinely unsettling for the astronomy community. Did this thing form like a normal planet? No, because the composition is entirely different, said Zhang. Did it form by stripping the outside of a star like normal black widow systems are formed? Probably not, because nuclear physics does not make pure carbon. It's very hard to imagine how you get this extremely carbon-enriched composition. It seems to rule out every known formation mechanism. Read that again. Every known formation mechanism is ruled out. Scientists have two primary models for how a planet can end up in this type of system. It either formed as a planet through the normal processes of planetary formation, gas and dust collapsing around a star, or it was once a companion star that got stripped down to a planetary mass as the pulsar consumed it. Neither of those models produces an atmosphere of pure helium and molecular carbon, with no oxygen, no nitrogen, and no water. Nothing in our current understanding of how matter behaves, how stars evolve, or how planetary systems form can account for what is sitting in that data. To understand why this is so profoundly strange, we need to understand what a black widow system normally looks like, because that is the category of system that PSR J232-26550b belongs to, at least loosely. Black widows are a rare type of system where a rapidly spinning pulsar is paired with a small, low-mass companion. In the past, material from the companion would have streamed onto the pulsar, causing it to spin faster over time, which powers a strong wind. That wind and radiation bombard and evaporate the smaller and less massive star. Like the spider it's named after, the pulsar slowly consumes its partner. In a typical black widow system, what remains of the companion is a small, dense stellar remnant, a fragment of a former star, chemically consistent with what stellar physics predicts. But this object is not that. It is Jupiter-sized. It has a planetary scale atmosphere, and that atmosphere is made of something no one expected to find anywhere in the universe. The classification system we used to define black widow pulsars was not built with this object in mind. It sits somewhere between a planet and a dead star, in a category that does not officially exist yet. And then there is the shape. Gravitational forces from the much heavier pulsar are pulling the Jupiter-mass planet into a bizarre lemon shape. The tidal forces generated by the neutron star's extreme gravity are so powerful at a distance of just 1 million miles that they are physically deforming the planet, stretching it, pulling it into an elongated ellipsoid, a lemon. The same tidal force that creates ocean tides on Earth is, at this scale and proximity, reshaping an entire world. The equatorial diameter of this planet is measurably larger than its polar diameter because of the gravitational gradient across its body. And because it is tidally locked, meaning the same face always points toward the pulsar, the same way the moon always shows the same face to Earth. That deformation is permanent. The planet is frozen into its lemon shape, locked in a gravitational embrace with a dead, spinning, city-sized star that fires radiation beams at it every few milliseconds. This is a relationship that can only end one way. And it is not ending well for the planet. What makes the Webb telescope's observation of this system so extraordinary from a technical standpoint is the reverse of what you might expect. Normally, studying a planet's atmosphere is incredibly difficult because the host star is so much brighter than the planet that the stellar light drowns out the planetary signal. But this system flipped that dynamic completely. This system is unique because we are able to view the planet illuminated by its host star, but not see the host star at all, explained Maya Belesne, a graduate student at Stanford University. So we get a really pristine spectrum. The pulsar fires gamma rays and high-energy particles, radiation that Webb's infrared instruments cannot see. So from the telescope's perspective, the star is essentially invisible. Only the planet glows in infrared. Scientists could study the entire orbital arc of PSR J2322-265 in extraordinary detail, watching how its brightness shifted as it moved through different phases, much like watching the moon go through its cycles. And from those shifts, they extracted the atmospheric chemistry with a precision normally reserved for our own solar system. The universe had accidentally created the perfect laboratory. A planet so extreme it barely makes sense, made observable by the very deadness of its star. And when you look at the broader picture of what the James Webb Space Telescope has been doing since it began full science operations, this discovery takes on even greater weight. Webb was designed to look back in time toward the first galaxies, to peer through dust clouds at forming star systems, and to characterize the atmospheres of exoplanets. It has done all of that. But the discovery of PSR J2322-265b represents something that was not on the original checklist. This is a new type of planet atmosphere that nobody has ever seen before, and the discovery was only possible because of the James Webb Space Telescope's infrared sensitivity and unique observing conditions. This is not an incremental improvement on existing knowledge. This is a category of object that was not known to exist before Webb looked. It is the kind of discovery that forces scientists to sit down and rewrite the theoretical frameworks, not just update them. The carbon-rich nature of this atmosphere also raises questions that extend far beyond this single planet. Carbon is the backbone of life, as we know it. Every cell in your body, every protein, every strand of DNA, all of it is built on carbon chemistry. The question of whether carbon-dominated environments elsewhere in the universe could support some form of chemistry complex enough to be called life is one that astrobiologists have debated for decades. They have generally concluded that carbon-rich but oxygen-poor environments are hostile to life as we understand it. But our understanding of life is based entirely on a sample size of one, Earth. And the universe just showed us a planet with a carbon atmosphere that operates under conditions we had never even considered modeling. What does that mean for the search for life? What chemistry is possible in an atmosphere of helium and molecular carbon, compressed by the gravity of a neutron star, bathed in millisecond pulsar radiation? We don't know. We genuinely do not know. And that uncertainty is not a failure of science. It is an invitation. The implications for planetary formation theory are also profound. For decades, astrophysicists have built increasingly sophisticated models of how planetary systems assemble. They track the movement of gas and dust in protoplanetary disks. They model how gravity causes material to clump into planetesimals, then protoplanets, then full worlds. They have used these models to predict what kinds of planets can form around what kinds of stars, and those models have been largely successful. We have confirmed over 5,700 exoplanets, and most of them fit reasonably well into the categories the models predict: hot Jupiters, super-Earths, mini-Neptunes, ocean worlds, lava worlds. Each one strange in its own way, but fundamentally explicable by the physics we know. PSR J2322-265b does not fit. It cannot be explained by any version of any model currently in use. And that means either there is a formation pathway that no one has discovered yet, or this object formed through some sequence of events so rare and so unlikely that it represents a cosmic accident, a 1 in a billion outcome that our instruments happen to catch. Either possibility has enormous consequences for how we think about the diversity of worlds in the universe. What most people are not seeing in the coverage of this discovery is the deeper philosophical rupture it represents. Science progresses through a cycle of observation, model building, prediction, and testing. When an observation fits an existing model, it strengthens our confidence. When it doesn't, one of two things happens. The model is refined to absorb the anomaly, or the anomaly remains unexplained while scientists debate. PSR J2322-265b belongs firmly in the second category for now. The lead researcher himself stated that it rules out every known formation mechanism. That is not a minor amendment to existing theory. That is a known unknown, a named gap in human knowledge, hanging in the constellation Sculptor, 750 light-years away, orbiting once every 7 hours and 48 minutes, made of something no one expected, shaped by forces no planet should be close enough to feel. There is something almost philosophical about the timing of this discovery. We are living in an era when the question of whether we are alone in the universe has moved from the domain of speculation into the domain of active scientific investigation. NASA's astrobiology program is running. The search for biosignatures in exoplanet atmospheres is a primary mission objective for Webb. Missions like the Europa Clipper are en route to moons in our own solar system that may harbor liquid water beneath their icy surfaces. The entire infrastructure of 21st century space science is being rebuilt around the question of life. And in the middle of that effort, Webb turned its gaze to a corner of the sky and found something that expanded the definition of strange so dramatically that scientists literally said out loud, on record, that they didn't know what they were looking at. That humility is not a weakness. It is precisely the kind of moment that historically precedes a revolution. And here is the thing that nobody is talking about loudly enough. "It's nice to not know everything," said Roger Ramani of Stanford University. "I'm looking forward to learning more about the weirdness of this atmosphere. It's great to have a puzzle to go after." That sentence sounds modest, but listen to what it implies. Well, one of the world's leading experts on this type of pulsar system, a man who has spent his career mapping the behavior of Black Widow pulsars, looked at this planet and said he was looking forward to learning about its weirdness. Not explaining it, learning about it. The distinction matters. Scientists do not say things like that when they are on the verge of solving a problem. They say that when the problem is new enough that they haven't even assembled the right vocabulary yet. They are not at the stage of finding the answer. They are still at the stage of understanding the question. The Webb telescope will continue to observe PSR J23222650b. More time on this system has been allocated, and future observations will attempt to pin down the atmospheric chemistry more precisely, looking for trace elements, measuring temperature gradients across the orbital arc, hunting for any signal that might suggest where all the oxygen and nitrogen went, and why the carbon survived in molecular form at temperatures where it should be reacting with everything else. Theoretical physicists will meanwhile attempt to build formation models that could produce this outcome, working backward from what Webb found towards some hypothetical history that could explain it. That is painstaking work. It could take years. And the answer, when it comes, may require concepts that don't yet exist in the textbooks. In the meantime, the planet continues its relentless cycle. At just around 1 million miles from its pulsar parent star, PSR J23222650b completes an orbit once every 8 hours or so, and its lemon-like shape emerges from tidal forces generated within the planet by the powerful gravity of the dead star it clings to. Every 8 hours, a full year. A world of diamond rain and carbon skies, shaped like a lemon, scorched on one face and merely burning on the other, being slowly consumed by a city-sized object that spins 300 times a second and has been dead for millions of years. If you tried to write this as fiction, an editor would send it back. Too implausible, too extreme, too far outside the parameters of what readers would accept. And yet, it is real. It is measured. It is peer-reviewed and published in the Astrophysical Journal Letters. It is sitting in the sky right now, 750 light-years away, doing exactly what it has always done, existing in defiance of everything we thought we knew about how the universe works. The real question this discovery leaves us with is not just about this planet. It is about the 5,700 planets we have already confirmed, and the billions more we have not yet seen. If one world this extreme, this chemically bizarre, this structurally unprecedented can exist, and exist close enough for us to find it, what else is out there? What other categories of planet are waiting in the data that no one has collected yet? What formation processes are operating in corners of the galaxy we haven't aimed our telescopes at? The universe has always been stranger than we imagined. It has never once failed to be weirder, more violent, more creative, and more indifferent to our expectations than we were prepared for. PSR J23222650b is not an exception to that rule. It is the latest confirmation of it. And here's what stays with you long after the headlines fade and the press release disappears from the news cycle. Somewhere in the southern sky, in a constellation named after a sculptor, which feels almost too appropriate, there's a world that no one expected. A world that broke the models on the day it was found. A world shaped by forces so immense they bent its body into a curve, wrapped in clouds of soot that condense into diamonds in the dark, orbiting a dead star so fast that a year passes before most people finish a workday. It has been there for a long, long time. It will be there long after us. And it carries within its impossible atmosphere a single, stubborn, humbling message from the cosmos. You do not know me yet. You have not even begun to know me. And whatever you think the universe is, whatever models you have built, whatever categories you have assigned, whatever certainty you have settled into, there are things out here that will take all of that apart, quietly, in the data, while a team of scientists stares at a screen and the most honest thing any of them can say is, what the heck is this? The answer is still being written, and it is going to change everything.